Welcome back to the channel. Today we're going to solve the problem I to the power of pi. We will take a small detour along the way so that you can see how to solve similar problems in the future. First, let's look at complex numbers. They are represented on a graph with a real part on the x-axis and an imaginary part on the y-axis. In vector form, you can add these to make the total complex number. For example, 1 plus 2i has a real part 1 and an imaginary part 2i. On the screen we have the real part represented by the yellow line, the imaginary part represented by the red line, and the total complex number represented by the orange line. Since the vector and its real and imaginary parts make a right angle, we can use trigonometric functions like sine and cosine to find the side lengths. For a vector of length 1, these identities simplify and cos of theta represents the real part on the adjacent side, and sine of theta represents the complex part on the opposite side. Since we are on the complex plane, it's important to note that theta is the angle between the positive x-axis and the vector. Since any complex vector is just a scaled version of this unit vector, we can use r to represent the scaling factor and multiply all sides by r. Now we can see that a complex number in Cartesian form, x plus yi, can be represented in polar form using theta and the length of the vector r. You might have seen Taylor series before, but if not, then don't worry. A Taylor series is simply a way of representing a function as a polynomial, like x squared, x cubed, x to the power of 4, and so on. Usually you see them of power of x's, but in this case we use theta as the variable. The interesting thing about these representations is that if you replace the sine and cosine functions in the polar identity that we found, it's actually identical to the Taylor expansion of e to the z, where z is equal to theta I. So now that we have this useful identity, how can we use it to solve I to the power of pi? Well, first, let's find what I is, and then put it to the power of pi afterwards. The vector I makes a 90-degree angle with the positive x-axis, so theta equals 90 degrees or pi over 2 radians. The length of this vector I is 1, since the vector is 1i. If we insert the theta and r values into the identity, we get e to the power of pi over 2i, and you can find the values on the right-hand side very easily. But what about I to the power of pi? Well, if we raise e to the power of pi over 2i to a power, the power laws say that we must multiply the outer indice with the inner ones. This results in e to the power of pi squared over 2 times I. The final step is then to simply insert these values into the trigonometric part of the identity, and then we can evaluate them. Using a calculator, we can see that we have a rough value of 0.221 minus 0.976i as the answer. This method can be used to change the form of various different complex numbers, and it can be really useful for plotting them on graphs and finding their values. Thank you for watching. Remember to like, subscribe, and turn on the notifications for this video if you want to see more maths videos like this one covering topics like number theory, maths history, and various other maths topics.